Okay, so for this question, we have this diene, and we're reacting it with HBr. We have two double bonds that can react with the proton to give us a carbocation intermediate. So let's first consider this top double bond. If it picks up the proton, we can put the proton at this position or at this position, giving us two potential carbocation intermediates. We could have that. Or that. Okay, now we can look at reaction with the other double bond and the proton to give us two different carbocation intermediates. Now if we examine all these, you should be able to cross out a couple of them for things that we really don't need to consider. So here we have a carbocation that is both resonance stabilized because it's allylic and it's tertiary, versus this carbocation that's not resonance stabilized. So we're not going to worry about this one. We're going to form this lower energy resonance stabilized carbocation. The same goes for these two. We're not going to form this one because it's not resonance stabilized. This is the only one we're going to get. From here, now that we have these intermediates, we always want to look at resonance structures. And for each of these, we can draw a resonance structure. The resonance structure for this is that, while the resonance structure for this is that. Okay, so now that we have these intermediates, we can think about what happens if we react these with the bromide anion that's floating around in the solution. So the bromide anion will attack the carbocation to give us product. So those are our four products. And as you can see with this first carbocation intermediate and its resonance structure, the two products are identical. Okay, so we have the 1,2 product, but it's the same thing as your 1,4 product. From our other carbocation intermediate and its resonance structure, we have a 1,2 product as well as a 1,4 product. And in this case, they're different. So essentially from this reaction, we form three different products, A, B, and C. Now if we were to do this reaction at room temperature, we would probably get a mixture of these three products. But we want to think about what happens if we were to do this reaction under kinetic control or thermodynamic control. So if we were to do this reaction at minus 80 degrees, the reaction would be controlled kinetically, which means we would only get these 1,2 products. So we would get products A as well as product B. So these are the products that form fastest. If we were to do the reaction at elevated temperatures, we would get the thermodynamic products, so the products that are overall more stable. So that would be product A as well as product C. And the reason these are thermodynamically more stable, if we compare product A and C to product B, A and C have a tertiary or a tri-substituted double bond, versus product B only has a di-substituted double bond. So in this case, one of our products, which is A, is both the thermodynamic and the kinetic product.